Okay. Today we will look at another data structure. Again motivated by a minimum spanning tree algorithm that also has a flavor of amortized complexity in the running time analysis. So, the motivation comes from implementing Kruskal's algorithm for minimum spanning tree. So, recall how the minimum spanning tree algorithm works for Kruskal's algorithm. Anybody? It's also another greedy algorithm. How does it work? Sort the weights of the edges. Okay. So, what is the minimum spanning tree problem? You have a weighted graph, weights on non-negative weights on the edges, and you want to find the spanning tree, right? A tree that spans, meaning touches every vertex, such that the total weight is the minimum among all such spanning trees, right? So, sort the weights in non-decreasing order. Right, the simplest greedy algorithm is we pick the smallest weight edge in my solution, go and pick the next smallest weight edge in the solution and keep going. When do you not pick an edge? If it forms a cycle with whatever I have already picked, then you do not pick. That is all the algorithm, right. So, I sort the weight in a non decreasing order, let E1, E2 up to EM be the order. Then the algorithm simply says for I going from 2, okay. So, let us initialize my forest, which is the solution I am trying to construct, to the first edge, and for I going from 2 to M, if EI does not form a cycle with edges of F, okay, this is the entire Kruskal's spanning tree algorithm. Just keep picking the next smallest weight edge, add it to the solution as long as it does not form a cycle. Again, why the algorithm gives you a minimum spanning tree requires a proof. We do not want to get into it. Hopefully, you have seen it. If not, please check the proof. Generally greedy algorithms do not give you optimum solution. We will see later for hard problems. It is one of the very few problems for which greedy actually gives you the optimum solutions. It requires an argument why that finally at the end the F what you have has the total minimum cost the smallest. But what we are going to look at is how do we implement this algorithm, right? And so this is a sorting step, so you can do it in m log m time. Now we want to think about how do we implement this step, right? So if you have seen this practice problem, worked it out, how do I check whether a graph has a cycle? How much time does it take to check whether a graph on n vertices and m edges, whether it has a cycle? How much time do you need? There is one problem in the list. How do you check whether a graph has a cycle? do a depth first search or breadth first search or something. As long as you encounter a vertex which you have seen before, you can keep going, and if you've seen something which you've seen before, you will have a cycle. Right? How much time does it take? Okay, but the question asks for something better. Order n. Okay, you can actually test whether a graph has a cycle in order n time. Please go and solve the practice problems. Okay, this is again a reminder for that. They are not out there for some archival purposes. We're going to keep using them. So please solve them, and you are welcome to discuss and come up with solutions. So you can actually test whether in this case the set of edges induced by f, whether it forms a cycle, in the worst case could be order n. So if you are very naive about it, this is going to take some order mn time. Right? So this is this part we want to improve by using some nice data structures. So let's see how do we implement, what is the question we want to solve here. So suppose EI is u comma v. So at any point of time, what do you have in your what do you have? The edges induced by the EIs, you have a forest, right? Because there is no cycle, so they induce a forest, right? And let's say my f is looking like this, right? Some tree, a collection of trees I have picked up at some point of time, and the new edge comes EI. When should I add and when do I not add it? So I want to rewrite this, moving towards implementation. What does it mean by after adding u and v at this edge uv, I do not have a cycle. When do you have a cycle? When do you not have a cycle in this picture? Yes, if u and v are endpoints of the same tree, then it forms a cycle, and if they connect two different trees, then they do not form a cycle, right. So if u and different trees of the forest we have, then you are going to add this, otherwise we do not, right. So now our data structure problem boils down to what sort of objects do we want to represent, so that we can answer this query fast, right. So what do we, so notice that you really do not need this tree structure stored for us. I mean, finally you need it for your output, but for the purpose of this query, what do you need? The set of vertices in each component, that is all you need, right. So if you, so this has, let us say, some A, B, vertex number 1, 2, 7, 5, 3, 2, this is 6, 8, 9, 11, maybe this is 4, 10, 12, 15, and so on. This is my tree. Then this tree structure is not very relevant for this query, because all it is asking is, are the endpoints into different trees. So all I care about is this vertex set, right. So what is it you want to represent? What are the objects you want to represent, and what is the query, right. So the objects you want to represent, you have a family of sets, right. These are all subsets of V, the vertex set. They are also disjoint. Right. Yeah. So, and what are the queries you want to support? So, the data structure problem we have is represent this to support what queries? What are the queries you want to support? Yes, given an element, which subset does it belong to? I need to know that, right? Because basically I will check that query on U and V and see whether they belong to the same subset or do they belong to different subset. So, what is the query? Find set for X in V. So, let us assume that this family actually spans the entire vertex set. So, okay, so they cover my V, and again without loss of generality I am going to assume that my vertex set is N, right. So, if this collection of sets do not cover V, I will add some enough singletons. Okay, so, this family for example is going to look like so, this is a family of subsets of 1 to 11. Have I missed anybody? Okay, 1 to 12, okay. And I have singletons and they cover 1 to 12 everything. So, now given some I need to represent them somehow, that is my goal. Given some X, I need to know which set it belongs to. What other query do I need to support? Okay, where do I do the union? In my algorithm?
If the edge U and V, if the vertices U and V belong to different trees and we include that edge, then those two trees should be combined.
Exactly, right. So, that is another query we want to support, because it is not just about testing whether they are in different components, same component. If they are in different components, I am going to add it to my solution, and so now these two trees are merged into one single tree. So, now I have to take the union of these two sets, right. So, union, some Si Sj, these are sets in my, these are the two operations I want to support efficiently, okay. So, typically if you would have seen, right, algorithms plus data structures is equal to program, right. So, we start with a very simple version of minimum spanning tree algorithm. We need to make sure that it is a correct algorithm. Now, we are gradually modifying things to implement it. Towards implementation, you abstract out what are the kind of queries we want to support that keep happening again and again, and then that will take you to the data structure question. Now, we can forget about Kruskal's algorithm and worry about supporting these operations efficiently. Okay. Right. So, in fact, these are important. You can also think of somehow you want, you have a graph which is changing and you want to dynamically maintain connected components. Okay. So, another application, for example, for these operations is that you have a graph where the edges are coming in. At any point of time, I want to know what are the connected components of the graph, right. So, again you maintain the sets of the connected components. When this edge joins two connected components, you have to make union of these two sets. Okay. So, now let us spend rest of the day and maybe tomorrow trying to come up with some implementations. So, this is our data structure problem, right. I want to represent a family of disjoint subsets of 1 to n, and you want to support these queries. Now, often when you want to do a union, you are given the sets, or maybe you are just given some elements, you have to find the sets and then do a union. So, we will make it clear when we implement these. And how do we represent the sets? Basically you can store one element as a representative of each set, or you can give them a separate name or give one element of each set as a representative. So then you want to know that two elements belong to the same set, you just run through and see whether they have the same representative or not, right? Okay. Okay, so let me start with something very simple representation. I have an array S and I store, so my elements are 1 to n, right, because I assume that my vertex set is 1 to n. So I am going to say Sy is a set containing I, right, whatever. So if you want to represent it by one of the elements, store that representative, or if you have a name for the set, store that name. So this is my starting point data structure to support this, right? And let's gradually add things to it, and then we'll see how we can improve it. So if that's all I store, how much time does it take to do find set operation? Yep. Order 1, constant time, right? Because I just index S, go to S of x, and it gives me the set it belongs to. But just array, so constant time. But if I want to do union, let's say I say set containing x, and this is a set containing y. So in order 1 time I find the set containing x, order 1 time, say let's say x belongs to some set number 3, y belongs to set number 7. I want to do a union of the sets 3 and 7, what should I do? Go through the entire array and change the 3s to 7, for example, wherever there is set number 3, whatever. So look at, maybe the x belongs, so run through array S and change the name of the set containing x to that of y, right? Or I could just change the set containing y to that of x, right? Now, heuristically, which one is better to do? Smaller? Yeah, smaller size. Okay, I mean, everybody is thinking, because it's not really going to help, because you have to run through your array and check in linear time who has this anyway. But let's start with smaller. So how do I know which one has a smaller size? Let's add that also in my data structure, right? So I'm going to add another array size of I for every set I, size of the set. Some sets may be 0, some sets may have some number. Suppose I store this array. Then if you ask me, if you want to do a union, I'll just go and check x, go index into y, go to those sets and see which one has the smaller, and change the smaller guy's name to bigger, but I still have to run through my array and find them, right? So actually, let's do an example. So let's see, can I avoid running through the entire array? Maybe you store this by linked list or something, right? So let's do it on the. So if this is my family, then my array S will have 1 to 12, I said, okay. And let's say I give this names 1, 2, 3, 4, 5, 6 sets. So 1 is in 2, 5 is in 2, 3 is in 3, 4 is in 1. Okay, so that's my arrangement of S. Then I have another array size, which will simply say size of 1 is 2, size of 2 is 3, size of 3. So this is my data structure so far. So now if you say, union 2 and 5, I first index and see that 2 is in set number 2, sorry, not 2 and 10, I meant. 2 is in set number 2 and 10 is in set number 5. So I have to go and change all the 2's to 5 or all the 5's to 2. And I look up and see that 5 actually has only one element. So I decide to change all the 5's to 2, but I have to quickly find them. Okay. So let me add more data structures. Let's say the first of this set. So in a sense, I am going to now represent each set in a linked list. Okay. So the first element of set 1 is 1, first element of set, first element of set 1 is in position 1, first element of, okay, right, first element of set 1 is in position 4, first element of set 2 is in position 1, first element of position set 3, first element of set 4, first element of set 5 and first element of, okay. So this is I store this. So that means if you want to know where is the set number 5, it takes me directly to this position, but I have to change all the 5's to 2 to do this. I have to go and find the next 5. So let me add another array here. Which tells me an index. What is a linked list, right? It's just a position. So next tells me where is the next element there. Right. In this case, it will simply say nil because there is nobody else, so I can stop. Otherwise, it will take me to the next 5. I go and change that to 2. It will take me to the next 5, change that to 2, and so on. So in this process, find set still remains constant time, but now I can perform union in how much time? So find set in the worst case, in the worst case order n, but more precisely if you want to say it is proportional to the size of the smaller set, right. Everybody with me? Because first I have to find the smaller set, the size array will tell me that. So now I decide that I am going to change the label of the smaller set. So the first array will tell me where is the first set there, the next pointers will tell me where the next element are, and I keep changing. There are a few more things you have to do, right. After you do the union, you have to update the sizes, because if two sets have become smaller, then one has become bigger and the other has become 0. You have to update that, but that is all some constant time. The first of that set will change because you have done the union, right. The next pointer of something will change because you have merged two linked lists, but all that can be done in this time. So I am going to say that size of the smaller set. Okay. Now, so in the worst case, it could be as bad as n, right, but what do we expect? Amortized, right, because remember the set it takes a while for the size to become that large, because we are starting with sizes of 1, right, because when we initialize the Kruskal's algorithm where forest had only one element, so there was one set, or maybe even forest is empty, every set was a singleton set. We are starting with sets of size 1, and we are gradually building up to sets of size n, because finally you have a tree and it will be sets of size n, and you are always doing union of the smaller sized set. The time you spend is proportional to the size of the smaller set, right, including for all the bookkeeping operations you would want to do here. So worst case, because your set can be as large as n by 2 or even more, no, n by 2, right, because if you have a larger set you would have merged a smaller set, so the time is smaller. So now I want to claim that the amortized complexity is it's like a puzzle. You start with a sequence 1 1 1 1 1. At any point of time you are taking some two numbers and adding them, and the time you spend is proportional to the smaller number. Finally you reach n. What is the total time, right? So I claim, so even though union in the worst case takes order n time, so starting from n singletons, and if you perform m union operations, so also notice that sometimes the union takes constant time, because you find that these two elements are in the same set, you do not have to do anything. So the cost is just finding that out, right, that is just constant. M union operations, spending time proportional to order size of the smaller set, then the total cost so it is not n square, but or even mn. Okay, clearly you are not doing m union, m is bounded by like n minus 1, right, because after that or beyond that union operations are going to find out that these two elements are in the same set, because after every union one set comes down in your family, and you start with n sets and you are going to get down to a set of size n. So essentially all I am claiming is that the amortized complexity of your union is only log n, okay. And it is important that for this that you are actually spending time proportional to the smaller size set, okay. Is it easy to come up with an example that if you actually spend time proportional to the largest set, you might hit n square? Exactly. So suppose you built it up so that there is one set of size n by 2, and then you are merging this singleton with this set. And if I spend time proportional to the larger set, then I am going to spend n by 2 for that, and for each subsequent merge is going to take me n by 2 times. So it is like at least n by 2, so it is n square. So it is important to note that I am spending time proportional to the size of the smaller set. Okay, this actually is a one line proof. So let us see if there are any ideas before I spoil the fun, right. So what are we doing? I mean, what am I counting? I mean, there are some bookkeeping operations, changing these pointers and all that is fine. That's all, hidden into this, whatever the total time. But what is the real cost and what am I counting? I mean, in the union operation, what really happens? Label. Yeah. So we are changing the name of the set. So that's exactly what I'm counting. There's nothing much, right? Everything else can be subsumed into this count. So all we are counting is number of times the set label changes overall. Okay. Given that, now so we start with set label of any element. There are n elements, and in union operation, some label changes. For one of these elements, for several of these elements, the label of the set changes. Now I want to count the total number of label changes for all of them. Okay, and I want to claim that that total is n log n.
For every element, to find it, we take log n time.
No, finding actually take only constant time. So don't worry about that. That's not. That's why I said we are only counting about the label changes. Okay, you have to connect the size of the set and the label change. Okay, I'll just tell you one line, everything will follow. Right. So my label changes from 3 to 5 or whatever, right? When I am an element, and when my label changes, what happens to the size of my set? By how much? Can you say some bound for it? At least doubles, right? That's it, right? Everything else will follow, right? Once you see log, you know where it should come from, right? When the label of element changes, right? First of all, it gets into a larger set, but not just some larger set. My size of the set actually at least doubles, because why did you change me? Because I am merging with some other set which is larger, at least as big as mine, right? So when my label changes, the size of my set from whatever it was, it doubles. Right? That's it. That's a one line proof, right? So we will count the label changes. Label, what is the label? Label of the set. During union operation. Okay, so I don't know whether you would fit it into a potential argument. Maybe there is a way to argue this using potential, but this is sort of an overall argument here, right? Aggregate argument. Whenever the label of an element changes, it is merged, right? Its set is merged with the set whose size is at least as large. Hence, the size of the set it belongs to, hence its size basically, right? The size of, size of the set it belongs to doubles at least from what it was. So now you're sort of arguing this instead of arguing this union by union operation, we are arguing this element by element. if some elements set label, if some union touches me and changes me, that means the size of my set, if it was 4 before, it has become at least 8, maybe even more. Okay. So, how much can change? Because I start with one element set, my size was 1, and every time I am changed, my set becomes doubled, and I eventually reach a set of size n. So, I cannot do more than log n many changes, right. As their sizes start with 1 and end with n. Okay, so this tells you, this simple data structure where you can do finds in constant time. Union has an amortized logarithmic time. Okay, now we want to just switch gear, do some slightly different kind of data structures where okay, and we will see different complexities for find, and so in particular the max of these two in fact we will improve even better than log in the amortized complexity. Okay, so now this we are going to get a tree based implementation. So this is good enough for our Kruskal spanning tree, because anyway we spend m log m to sort the edge weights anyway, but as a data structure question, if I want to improve the max time for max of these two operations, we can do better actually. Now you might ask, what is better than log, right? Already log n seems like a good thing, but we will see some interesting functions here. So here what we are going to do is that each set is represented by a tree, a rooted tree with the root giving the label of the set. All right. So a singleton will be represented as the single node, x, and with, if you want to have a label for the set, and that is stored with the root. So at any point of time your set is a rooted tree, and the way we will build this tree is based on how we do the unions basically, right. So union of some S1 and S2 will make the root of S1 a child of root of S2, or vice versa, right. We will use some heuristics for it. So this is my tree S1 and my tree S2. So now maybe this would become the root. and this becomes the new label of the union set. Okay, I can make x1 a child of the root of s2, or other way we'll use some heuristics to do that. So, and how do I implement find? So, come back to your array thing. What basically what you have in your array is a pointer to its parent. That will completely specify your trees and everything, right? So, basically you have an array of pointers. It points to its parent because every node has a unique parent. So, it will point to the parent. It could be itself if it's a root. So, now if you ask me, okay, which set does 7 belong to, what do? Just traverse the parent, go all the way up to the root, and you will get the label, and that is the label of the set, right? If you want to know whether two sets belong to the same, two elements belong to the same set, traverse both of them, and they both reach the same root, they belong to the same set, otherwise not. So, now the time you will spend for find set is proportional to the height, right. So, now that tells me that somehow I want to minimize the height. So, I will do the unions carefully, keeping that goal in mind, right. So, whereas the union operation, if you know the roots, it just takes constant time. You just have to apply your heuristic and make this guy a child of the other. If you don't know the root, you have to traverse and find it. Okay, so what are some ideas to keep the height as small as possible? So, essentially there are two ideas: union by size, and another one it simply says union by height. Okay, so what do you do here? Keep the sizes of this set with the root, and make, so which one do you want to make the child of the other? The smaller one becomes the child of the larger one, or the larger one becomes the child of the smaller? Okay, make the root of the smaller set child of the other. If both have the same size, then do something arbitrarily, but otherwise make the smaller set the child of the larger. And here it's the same thing, you just keep the height. Keep the height of the tree okay. And the claim is that, what's the claim? If you do this, then if any of this, then why did you say the smaller the child of the larger? Okay. So, what would be the height if there are n nodes in the tree? Then if you do this size based heuristic, the height would be log n. Why? Because the same argument, right? The height, basically the height increases means what? The size doubles, right? It's exactly. No, is it not clear? Okay, so let me just, let's do it for the size, and height will also be. So the claim is, so like I'm going to, yeah, I called it a little union by size. If we do unions by size, then the height of a tree containing n elements I mean, you can prove by induction basically, because as you start with, the size was 0, height is 0, or no, size is 1 and height is 0. And okay, I mean, the way to prove is that if the height is k number of nodes in the subtree, what do I want to show? At least 2 power k, right? So you prove this by induction. Right? The corollary of all this is that the fine set operation takes order log n. Worst case, if we do union by size or height. Okay, so there is one other idea which we want to exploit and argue about the amortized complexity next time. And here is where the whole point of amortization comes in, right? So the point is that if you are anyway spending some time, why not spend a little bit more time so that it helps the future operation, right? That's the whole idea. So there is this idea of path compression. Again, this is all of this analysis. I mean, so far it's all easy stuff we have done in a logarithmic worst case. I mean, we got stuck, but I'm sure you'll be able to think a little bit and figure out the proof, or maybe we'll come back to it after I say this. So the idea is that, so we are going to again represent the sets by trees. Unions are going to be that you make one root the child of the other based on whatever heuristic you want to try. But when you do fine set operation, what are we doing? We start from some node and we keep going through its parent. Eventually you reach the root and say that that is the label of the set. At that point, what we are going to do is to make all these guys a direct child of the root. Okay, any node that comes in the path, we are going to make it a direct child of the root. Okay, so so the extra time is not much, right? You're going to, when you can implement it more or less the same time. As you find its parent, you just change its parent to the root. Okay, I haven't found the root yet, so you can go all the way and then come back and do a 2-pass algorithm, let's say, right? So you keep finding its parent, you found the root, remember the root, and then you come back and make all the parents of these guys the root as the parent. Okay, clearly that's going to help. I mean, it's not going to affect find set operation anyway, sorry, the union operation, because it's just combining the roots, but you expect that it will help the future find operations, because any find on this path now it's going to take constant time. Unless these guys, this has become a child of another and so on, but certainly it will speed up. But how do we capture the speed up and analyze it is the challenge. Okay, I mean, it requires a 1 hour of argument to show that union by height plus path compression results in an overall time of okay. So, let me write here. I may want to come back and prove this. So, union by height. So, the path compression idea is clear, right? Whenever you execute find set operation, follow through all the way, found the root, output it, and then make every node in the path as a child of the root, right? So, union by height plus path compression. Okay, so now one other question is, what is its height? Because now how heights of these nodes are going to change. So we won't bother updating the heights after you do this. So I'm going to give it a different name. I'm going to call it rank, which is the original height if you don't do the path compression. And if you don't do the path compression, they remain as what it was before, but they don't correspond to the height, because we have changed the levels of these vertices. If you do overall time of m alpha n, where this is called inverse Ackermann function. Okay, I don't know how many people have seen an Ackermann function, which is a very, very fast growing function, and this is the inverse of that. So it's pretty much almost a constant. Okay. So without even even just defining Ackermann's function and saying something about it will take some time. So what I will do is something weaker. Bound of m log star n. Okay, what is m and n? I hope it's clear. M is the number of unions you are doing, and n is the number of elements. So you start with n singletons. And what is log star n? So it is still a growing function of n. It's not constant, but for all practical purposes, it's constant. Okay, so log star n. Okay, what is log kn? It's basically log iterated k times. Okay, so log. You have some k many logs and n. So, for example, so what is log star n? Well, the limit. How many times you have to take log so that the resulting number becomes less than or equal to 1. And I mean, let's see for some small numbers, right? So for n equal to 2, what is log star of n? 1, because you take log n, it becomes 1. So, of course, the logs are all base 2, right? I didn't say it, but it's hopefully it's clear. So, if you do 1 log, it becomes 1. So, it's what about for 3? Okay, so, for 2, it's 1. For 3, log n would be 1 point something. So, you need another log to bring it down. For 4 also it is 2, because log 4 is 2, another log will make it 1, right. For 5, 6, 7, 8 it will be 3. For 9 to 2 power 8 actually, no, or sorry, 2 power 4. So, it is 9 to 16, okay. Because log 16 will be 4, another log will make it 2, another log will make it 1. So, for 16 it is actually 3, right. So, in fact, here it is 5 to 16 it's only. No, because what is log of 16? See, log 16 will make it 4, log 4 will make it 2, log 2 will make it 1. So, you need only 3. So, from 5 to 16 it is 3, from 17 to 2 power 16 it is actually 4, and you can see that it is how slowly it is growing, right. And for 2 power 16 it will be 5. So, it turns out for a n up to the number of particles in the universe or something, it is at most 5. Okay. Of course, for larger n it does grow. So, it is not constant, but for all practical purposes it is constant. So, I am talking about log star n. Alpha n grows even slower, okay. Its inverse Ackermann function grows even slower than log star n, and we will see next time tomorrow a proof, hopefully, that I'll try and show this log star n, okay, and using some potential or an aggregate method where we will say that first we will show that the union by height or size will, that alone gives you log n worst case, which we did not complete today. But in the amortized n, if you do this path compression, then the overall runtime is for m unions will take pretty close to order m time. Okay. I mean, why somebody came up with this function, I mean, it's still a mystery, and it's known that this is the best you can do. There is also sort of a lower bound, if somebody is up for it, I would recommend reading that paper. Under some conditions that omega m alpha n is necessary.
Log star n is the inverse of like tower of.
Yeah, exactly. So, it is the inverse of towers of 2. Yep. Okay, so tomorrow we will prove this first, at least one of the two, size or height, and then we will get into path compression and argue about this.